Okay, does anybody have any questions on what you did for homework? So we'll clear that up first. Yes, no? I'm going to record this for the 5 people or the 6 people that are gone. So when they come back tomorrow night or Sunday night, they can go online and listen to the video, right? The discussion. They'll be able to hear me and look at the goofy smartboard, but they won't be able to hear you unless you yell really loud. Mr. Bosque! Because the microphone is like right here, right? Okay, so 6.3. You're in your book, and the title says the properties of the trig function. So what are these properties? Okay, so when we talk about functions, if you think about your library of functions, the properties are domain and range, right? What is it, even or odd? Things like that. The graph, but we're not going to do the graph yet. The graph is in the next section. So the test on Wednesday will not cover any graphs. But if you want to start to look at those, you can. It sort of makes sense. For example, if I told you the graph of the sine function, if this is y is the sine of some angle, and this was the angle, and I told you that you could put any angle in that you wanted, and the graph looked like this, okay, and I told you that the top of this wave was at 1, and the bottom of the wave was at -1. Could you, just by looking at the picture, tell me what the domain was? What kind of angles can I put in there? Could I put in an angle of, let's say, 1,000 radians? No, I don't know. I've got a, let's see, I'm in radian mode. Here's the sine of 1,000 radians. Okay, so it comes out some number, right, 0.82. Could I put in 1,000,000 radians? What do you think the domain is? How big an angle could I put in? Domain are the values going this way, right? Infinite. Okay, good. So the domain, theta, could be any angle, right? Now that's sort of goofy to write it that way. So what's a better way of writing it? Theta could be, well, okay, interval notation. You can do that. -infinity to infinity, right? That's not really an ordered pair. That's an open interval. But another way of saying that would be all real numbers. Okay, so the domain for the sine function is all reals. Now you say numbers and you're thinking, well, wait a minute, that's an angle. We're going to get to that a little bit later. But you're right, you could put any number in to this function. Okay, so f of theta is the sine of theta. Now remember how that came about. When we were talking about the unit circle, so we've got this unit circle and we've got this point sitting here, and you're allowed to move that point around the circle, or you can put it anywhere you want, and you can move it around lots of different times. So if we started here and I said, show me an angle of 2 pi, okay, so where does 2 pi end up? Right where you started from, right? Because this would be pi over 2 up here, right? That's 1 pi. 180 degrees is the same as 1 pi, right? That's 3 pi over 2, 1.5 pi. And there's 2 pi. It ends up right back where it started from. Yes? By the way, what is the sine of 2 pi? Okay, so remember the 3 steps. The 3 steps are, I'm asking, what is the sine of 2 pi? So the first step is figure out where on the circle you are. There you are. What's the second step? Well, okay, we're going to get there in just a second, but before you do that, you got to know what the ordered pair is, right? That was the quiz. If you know all the ordered pairs, these are easy. So what is the ordered pair there? 1, 0. And then the third step is, what am I asking for? I'm asking for the sine, which is the y coordinate. So the answer is 0, right? By the by, if I were to label this axis up here, this theta axis, We're not doing graphs now. We're doing graphs in the next section, 6.4. But this point right here happens to be 2 pi. Okay? This point here happens to be at 1 pi. Okay? Anybody want to take a wild guess what the theta value is for right here at the top of the wave? Where is the sign first equal to 1? Where on the circle? How about that? Is it top, bottom, left, or right? Where's the sign equal to 1? Top of the circle, right? Because the sign was the y-coordinate. Yeah? Okay. So if we're moving our dot and we put it up there, by the way, what angle is that? Well, it's not 45 degrees. It's 90 degrees. It's 90 degrees, right? You're supposed to say right. Yeah, see, that's right. No, okay. Pi over 2? Pi over 2, yes? Okay, so if I said what was the sign of pi over 2, just by looking at your circle, you would say, oh yeah, that's up here at the ordered pair is 0, 1. What's the sign? That would be 1, right? Because that's the top of the circle, and the y-coordinate up there is at 1. Yes? Okay, so this point right here corresponds to this point right here, corresponds to this statement. Now again, I'm not concerned about the graph as much, but as this point travels around the circle, will the sign value become 1 again? Yeah, every time you do a rotation. Every time you get to the top of that circle. So that's sort of an interesting question. What happens if I go to there? That's pi over 2. Yes, theta is pi over 2. Suppose I go all the way around and I get to there. How big is the angle then? It's 1 full rotation plus pi over 2. So what's the number? Okay, so let's do a full rotation. Oh, whoops, I only did a half rotation. How many degrees was that? Half a rotation, 180. And what's the same number as 180 degrees? Pi, yes? Okay, so if I do a full rotation, that's 2 pi's. And maybe we should write that down. Full rotation is 2 pi. Okay? So go back to this picture. If I've gone to there, which is pi over 2, and then I do another rotation after that, that's pi over 2 plus 2 pi, which adds up to, hopefully you can do fractions. Yeah, that's 5 pi over 2. 5 pi over 2. We're back at the top of the circle. Right? Can we get to the top of the circle again? Okay, so we just go around again, right? We go around another rotation, we're back at the top. You know what the sine value of that angle would be? The sine is the y-coordinate. That would be 1. Well, like, this is sort of like, duh. Every time you go around, the sine value becomes 1. And this is sort of an interesting phenomenon. At the top of these waves, the sine is always 1. 1, 1, 1, 1. It just repeats. Okay, so this is the first function we've seen that does that. Whenever you have a repetition like that, it's said to be periodic. So the sine function is a periodic function. So yeah, when we're talking about, you know, these properties of the functions, we're going to worry about domain and range, right? We're going to worry about even or odd. And by the by, if you just look at the picture, can you tell me whether that's even or odd? It was on your last test, by the way. It's odd just by looking at the picture, right? Because it's symmetric about the origin. So yeah, this is odd, but it's also periodic. Now, again, this term periodic, we're going to have to investigate a little bit more. But if I were to take this section of this wave, this black section, I can sort of like, it's copy and paste idea. So like we're doing some sort of digital image. Take that, move it, there it is again. Move it, there it is again. Okay, so this picture just gets repeated again and again and again because you're going around the circle, around and around and around and around. Periodic. Okay, and that's the whole, you know, la-di-da-di. When you think about, you know, period, the tides, they rise and fall, right? on a regular basis. There's a high tide and there's a low tide, and there's a high tide and low tide. The sun rises, sets, rises, sets. Now we don't see the negative part, right? That's night, but it rises and it sets. There's a lot of periodic phenomena, and because of that, these trig functions have a lot of applications, and we'll look at applications later. Right now, we're just looking at sort of the properties of these things. Okay, so let's go back and think about domain and range, and we'll talk about this period. So we're looking at the sine function, and you are allowed to put in any angle into the sine function. That's legit. So our domain, we're going to say, is all reals, all real numbers. If you want to do it negative infinity to infinity, that's okay as an interval. If you wanted to very explicitly say, this is my angle, I'll call my angle theta for something. And yeah, the angle theta could be any positive or any negative number or zero. And by the by, if you're on the unit circle, where is zero? Top, bottom, left, or right? Where is zero? 0 degrees or zero angle. It's on the right-hand side, yeah? So if I said, what was the, sine of 0, you go, okay, that's 0 radians or 0 degrees. They happen to be the same. So that's over here on the right side of the circle. The ordered pair is 1, 0, so the sine of 0 is 0. And sure enough, that's what you see in this little diagram, right? The sine of 0 is 0. It goes right through the origin, the little wave picture. Okay, how about range? Now, range, you're thinking this vertical extent. If I have the picture, it's easy. What's the range? What's the lowest the wave gets? -1, and highest? 1. Okay, so we could write that pretty quickly. The range is all the values from -1 to 1 inclusive, right? So the sine of theta will always be less than or equal to 1 or bigger than or equal to -1. So that's a legitimate way of doing that. It doesn't matter what the angle is. Here I put in 1,000 radians on my calculator. Here's the sine of -332.158 radians. And sure enough, the sine is some number between -1 and +1. And that will always happen. So far, so good? Okay, so domain and range. Again, we're talking about the sine function here. From the picture, you can say it appears that the sine of theta is an odd function. Okay, but we're going to be a little bit more careful than just say, well, it looks odd. It is odd, by the way. The sine is odd. And I suppose we should have function notation here. How about f of theta is equal to the sine of theta is an odd function. So f of theta is the sine of theta is an odd function. Let's go back to the unit circle for a minute. So let me just throw a picture of a circle and think about angles. Because, we're doing theta is an angle. So we're going to take this dot and we're going to move it up to a certain level like that. And this will be the angle that we make, and that'll be theta. What does a negative theta look like? Well, positive rotation is that way. What's negative rotation? Going the other way, right? Okay, so here's a positive theta, this green one. If I started here and did negative theta, I'd go the other way, yes? Okay, so that would go down like this. And this is negative theta. Okay, so negative theta goes that way, and positive theta is going this way. Okay, and what do you notice about these blue dots? I'm going this much going up and that much going down, exactly the same amount. What about the two blue dots? Is anything the same about their coordinates? The x coordinates are the same, right? Okay, so let's see. This has some x number, right, and some y number. And this x number is exactly the same. How about the y number? What do you think? It's exactly opposite it, right? Okay, so the y down here is the opposite of that y. Okay, now let me see if I can write this out in function notation and see if this makes sense. If I have the sine of theta and I have the sine of negative theta, here's the question. Are they the same? Is the sine of theta the same as the sine of negative theta? Are the y coordinates the same? Say no. Got to yell it real loud so they can hear. Come on, Cat, you can do this. Cat doesn't have a big mouth today. I don't know. It's like, okay. No, of course not. They're not the same. How are they related? Is this y coordinate related to that one in any way, shape, or form? It's the opposite. Okay. So the sine of theta is the opposite of the sine of negative theta. You could put that or put it here. It doesn't matter, one or the other. Usually we see it this way. Okay. So that's the relationship between the sine of an angle and the sine of the opposite angle. Now, if you go back to the definitions way back, whenever you did that back with Dr. Hebert, if you've got f of negative theta, or usually we used x back then, f of negative x is the opposite of f of x. That was the definition of an odd function. Okay. So you might want to find that in your book, wherever odd function is. This, in fact, is an odd function. And the symmetry is pretty obvious. If I gave you the graph, there's the graph. It is symmetric about the origin. Okay. So domain, range, we got that. We know it's an odd function. Let's do one more thing about this period before we leave the sign. Again, the sign repeats every rotation. So that section can be repeated there. And how far is it before it starts to repeat? What's this distance from here to here? And you go, well, this is the origin. He told me this was 2 pi. This repeats every 2 pi, every rotation. Right? So the period for this thing, we're going to say the period is 2 pi. Okay? Now let's see how that plays out with calculations. Suppose I said, tell me the sine of, I don't know, let me pick a really, really big number, like 381 pi over 2. And you go, oh, golly, I don't know how to do that. Okay. But we got to figure out where on the circle you are. And once we know where the circle, top, bottom, left, or right, by the way, this is a quadrantal angle. It's either going to be the top or the bottom. Okay, I know that. And so either the sign is going to be +1 or -1. What is the sine of pi over 2? What is that? Okay, where are you on the circle? You know, go through the thought process. Where's pi over 2? Top of the circle. Ordered pair is 0, 1, right? So the sign is 1. We know that. That was your quiz. I hope you got that one. Well, actually, I didn't ask what was the sign. I just said, what was the ordered pair, right? Okay, so what is the sign of pi over 2 plus 2 pi? So now I'm going to the top of the circle, and now I'm adding another whole rotation. What's this? Where am I on the circle? I'm back at the top, yeah? So what's the sign? That would be 1 again. So this is also 1. What is the sign of pi over 2 plus 4 pi? Yeah, this is going to get pretty boring pretty quickly, right? I've added maybe I could do it this way. There's a rotation. There's another rotation. You know, so pi over 2, straight up. Add 2 pi, straight up. Add another 2 pi, straight up, right? Okay, so let's see what this is. This is, what, if I just sort of clean this up a little bit, I have pi over 2 plus 4 pi over 2 plus another 4 pi over 2. Okay, so what's that, 8? That's 9 pi over 2, sine of 9 pi over 2, and that's 1. Okay. Yes? No? Maybe so? Okay. We'll do one more and then we'll jump to the calculator. Actually, we can do it without a calculator, but what is the sine pi over 2 plus another 2 pi over 2? Let's write that as 4 pi over 2. This is top of the circle. This is a full rotation. Yeah. Okay, and here's another full rotation. And here's another full rotation. Okay, so I'm asking what is the sine of, what's that, 4, 8, 12, 13 pi over 2, and that's going to be 1. Now, the thought process here is, if I can figure out how many full rotations are in here and take those away, then I know where I am. I'm either going to be at the top or the bottom. So how might I do that? Any ideas? This sine of 9 pi over 2 is exactly the same as the sine of 1 pi over 2. This sine of 13 pi over 2 is exactly the same as the sine of 1 pi over 2. Okay, so how does the 13 turn into a 1? Or how does the 9 turn into a 1? Or how does, what was this? This is a 5 pi over 2. The sine of 5 pi over 2 is the same as the sine of 1 pi over 2. So how do we make that happen easily? 5 turns into a 1, 9 turns into a 1, 13 turns into a 1. I'll give you a hint on the next one. 17 will turn into a 1. 21 will turn into a 1. Anybody? Are you awake? I want a holiday. What's going on here? Let me just write down those numbers. 1 pi over 2 turns into 1 pi over 2. 5 pi over 2 turns into 1 pi over 2. 9 pi over 2 turns into 1 pi over 2. Right? 13 pi over 2 turns into 1 pi over 2. Say again? It's going up by 4s. Okay, so far so good. So there's something to do with 4. By the way, what is 4 pi over 2 in terms of rotations? That's 2 pi, which is, that's one rotation. That's the period, right? So this just keeps repeating every 4 pi's over 2. So again, this is my problem. I have this number, wherever it went to, right here, 381 pi over 2. So how am I going to figure out where 381 falls in this list? So 381 pi over 2. It's either going to be pi over 2, I'll tell you that, or it might be negative pi over 2. I'm either going to be at the top or the bottom. How do I know? Now, you said it goes up by 4s, right? Let me give you one more hint. If we had 21 pi over 2, that's going to end up at the top of the circle. But if I had 23 pi over 2, that's going to end up at the bottom of the circle. What's the difference between 21 and 23? We're going up by 4s. Okay. But if I said 47 pi over 2, where do you think, top or bottom? It's actually going to be the bottom. So sad. How do we know? Okay. Bingo. So what's this multiple plus 1 idea? That's division. Watch. What's 9 divided by 4? 2, right, with a leftover of 1. What is 13 divided by 4? 3 with a leftover of 1. Right? What is 23 divided by 4? Long division now. 4 goes into 23. How many times? Golly day, you guys really are awake. 5. With a leftover of 3. Now, I said it was supposed to be the same as negative pi over 2, but this says it's going to be 3 pi. 3 pi over 2? Question mark? Same thing. right? Same thing. So, I mean, here's your circle again. If I said, show me where pi over 2 is, you'd go, okay, pi over 2 is 90 degrees. I go there. Got it. If I said, show me what, well, we're doing this, 3 pi over 2. So 3 pi over 2. There's 1 pi over 2, 2 pi's over 2, 3 pi's over 2. And if I said, show me where negative pi over 2 is, you end up at the same spot, right? Okay, so if I did that, and if I said, what was the sine of 23 pi over 2, you'd say, okay, let me divide by 4. Look at the remainder. The remainder is 3. And so it's the same as 3 pi over 2, top or bottom of the circle. Sine of 23 pi over 2 is? Go ahead, be brave. It's either going to be positive 1 or negative 1. Take a pick. Negative 1, you're at the bottom of the circle. Okay? You'll get some practice on this on the homework. You'll see some of this periodic type behavior. If I wanted to go back and do the problem that I'm dealing with, this 381 over 2, just divide it by 4 and look at the remainder. So, I mean, I said you could use your calculator. Here's 381 divided by 4. 381 divided by 4. What's left over? Is it 1, 2, or 3? It goes 95 times with 1 left over, right? Okay. So this is going to be the same as pi over 2. Now, this statement is sort of bogus. Those numbers are obviously not the same, but the location on the circle is the same. Both of these are going to end up at the top of the circle. Okay, so what is the same is the sine value for these guys. And so if I said, what is the sine of 381 pi over 2, and that's going to be the same as the sine of pi over 2. And hopefully we know the sine of pi over 2 is 1. Okay, so just a real quick, confirmation. What is the sine of 381 pi divided by 2? Okay, and it comes out to be 1. Okay. If you look in your book, there's a scary looking statement about periods. Let me give you a page reference. It's probably the most scariest thing that you're going to see. Yeah, it's on the top of page 397. 397. It says the sine of theta plus 2 pi k is the same as the sine of theta, where k is any integer. Okay? This is a statement about the period of the sine function. Somebody give me an integer, any integer. Give me the integer that's not positive or negative. 0. Okay, so if k is 0, what does this say? This says the sine of theta plus 2 pi times 0. Well, theta plus 0 is still theta. Sine of theta is the same as the sine of theta. And if I were in my best, Howard Simpson, I would go, duh, right? Of course. Give me the smallest positive integer. 1. Okay, suppose k was 1. What does this say? This says now the sine of theta plus 2 pi times 1 is the same as the sine of theta. Do you see the rotation here? Right, that's that rotation idea. So I don't know where theta is. Theta could be any angle. Let's put the dot over here. So here's my angle. I'll do it in red. Here's my angle. So this is theta. And if I said, do another rotation, just take that dot and move it. Oops, move the dot. All the way around, one more rotation, I end up exactly the same spot. Right? So yeah, this makes sense. And you can go around as many times. Give me the largest, now think here, the largest negative integer. What is the largest negative integer? Be brave. Say it again. -1, sure. -1 is the biggest negative integer there is. Right? I mean, you know, that sort of bothers some people. Here's -1, here's -2, here's -3. When we talk about relative magnitude, big numbers are on the right, small numbers are on the left, right? So we can say like 3 is going to be bigger than -1 because 3 is over here and -1 is over here, right? Likewise, we can say 0 is bigger than -2. 0 is on the right, -2 is on the left, right? Or in particular, we could say -1 is bigger than -3. -1 is bigger than -3 because it's to the right. And so the biggest negative integer would be -1. I mean, some people in their head, they go, he wants a big negative number. You're thinking magnitude big. But no, I'm thinking value big. Okay, where are we? Oh yeah, so the biggest negative integer being -1. If we throw that in there, this says the sine of theta plus, now remember the k is going to go right there, make that -1. So 2 pi times -1 is -2 pi is supposed to be the same as the sine of theta. Yeah? Okay, so let's look at that sort of from a rotation perspective. Here's my circle. I'm going to go a certain angle, call that theta. So there's theta. But now it says you're supposed to do -2 pi. So how do you think about your dot? Here's my dot. I've rotated it from the starting point to there. That's theta. But now I have to take away 2 theta. So how do I do that? Now remember, not take away 2 theta, take away 2 pi. 2 pi is 1 full rotation. What is -2 pi? I'm going to kill myself if I try to rotate that way. What's -2 pi? Rotation the opposite way, go the other way, right? So we've gone from here, we go theta there, but now it says take away a rotation, so we've got to go all the way around this way, and we end up exactly the same spot. It makes sense, right? So sure enough, this statement about sine is true. Okay, so I think we've covered everything you need to know about sine. By the way, cosine stuff, exactly the same. Cosine stuff, exactly the same. So here's a picture of the cosine wave. Now, even if you were asleep, even if you didn't have any trig, even if you were closing your eyes, you could probably tell me what kind of function this is. Even, right, because your ears are open. This is an even function, yes? Symmetric about the y. By the way, definition of even function, f of x and f of -x, are they the same for even functions, question mark? Yeah? Give me an example of an even function from algebra. Y equals the absolute value of x. Y is the absolute value of x is an even function. Here's the picture. If I go out to a certain x value, and that's the functional height, and I go the same distance going this way, do I get the same functional height? Yeah, they're exactly the same. And that's true with this cosine as well. If I go to a certain angle, and I find the function happens to be that much, and I go the exact same distance over here, the function is going to be the same value. Okay, so for cosine, we still have the domain and range are the same. Let's go ahead and just write them down. So we spent a lot of time on the sine, but I am going to tell you the cosine is exactly the same. F of theta is the cosine. Domain is all reals. You can put any angle in. Range is, again, from -1 to 1. This is an even function. that is the cosine of theta is exactly the same as the cosine of minus theta. If you're unsure, just look at your circle. Okay, so here's an angle, call it theta, there's the dot. Go exactly the same amount in the other direction. This is negative theta. What can you tell me about those two dots? What's the same about them? The x-coordinates are the same, right? Because they're one over top the other. So that's what this says. The cosine of an angle is the same as the cosine of a negative angle. It's an even function. Even function. The last thing we could probably do is the period. And by the way, it's exactly the same as sine. So I can say cosine of theta plus 2 pi k is exactly the same as the cosine of theta. Again, we don't need the picture at this stage, but don't go away yet. If I were to do this as accurately as I could, and I'm sort of sloppy, here is one cycle of the cosine. If I move that over, I get exactly the same picture. That wasn't a cycle. One cycle to there. If I move that over, okay. We're going to stop it here. Please read the section. We're going to pick this up on Tuesday. I'll give you some sample test questions on Tuesday, and then our test is Wednesday. See you later, alligator. Bye-bye. Have a good weekend.